Bismillah ar-Rahman ar-Rahim. Last time we were talking about Boolean algebra, okay, and the last example we did was to generate or derive the Boolean expression of a logic circuit, and before that we were able to sketch the logic circuit of a given Boolean expression, and for both cases we derived the truth table. The truth table is the unique representation of functions. And at the first example, we saw that this function, which is A, B complement or B, okay, can be thought of as just A or B, because both functions, this one and this one, do have the same truth table. You can see it from here, okay? Also, for this function, we have seen last time that it is equivalent to A, B, and C, okay? So this function here is nothing but A, B, and C. So what does this tell us? It tells us that we can somehow come up with a minimal representation of functions. So this function here uses a single 3-input AND gate, whereas this function here uses a count of 2 AND gates, each of 2 input, and 1 OR gate. So 3 gates versus 1 gate. Okay, so this is a big reduction in hardware. Okay, so simplification, okay, helps us save on hardware. So let's turn our attention to the basic identities and the duality principle of Boolean algebra. So what do we mean by the duality principle? So if you have an expression, a Boolean expression, and you would like to generate its dual, then you simply switch the ands to ors, these two lines, switch the ands to ors, and switch the zeros to ones, and the ones to zeros, of course, and the ors to ands, okay? So if you have a property like this one here, x ORed with 0 is equal to x. We know this from the identity, because the 0 is the identity element of the OR gate, right? Or the OR operation. So x ORed with 0 is x. This is the simplest identity that you can, the simplest property of Boolean algebra that you can say, okay? So how can we generate the dual of this expression here, or this property? Basically by following these rules. Change the AND to OR, and the OR to AND, ones to zeros, and zeros to ones, okay? So in this case, instead of needing to remember 2 columns of data, okay, you need to remember only 1 column of properties, okay? And then you can generate the dual of these properties, okay? And the dual will be true as well, okay? So let me create the dual for this one, and then you tell me how to create the dual for the next one, okay? So the dual for this is the letters will remain the same, x, and then the OR changes to AND, right? X OR 0 changes to x and 1, right? Is equal to x, which means that the 1 is the identity of the AND, which we have learned already as part of Boolean algebra, right? Okay, so this is one property and it's dual. Okay, what about the null property? X ORed with 1 is 1, okay? So if you have 1 in the OR gate, okay, 1 ORed with anything is 1, regardless of that thing, whether it's a 0 or a 1, right? Because the OR gate works this way. If one of the inputs is 1, then the answer is 1, okay? So we have x ORed with 1 is 1. So who can tell me the dual of this expression?
X and
X
zero.
and 0.
Excellent. X ANDed with 0 is
0.
0. Again, if you remember the definition of the AND gate, If one of the inputs is 0, then the output is 0 regardless of the other input. Okay, so this is true as well. Okay, idempotence. What about idempotence property? It means that x ORed with x is x. So if you take something and you OR it with itself, you get the same thing, right? If it was a 0, you get a 0. If it was a 1, you get a 1. Okay, so it's x ORed with x is x, and the dual of that is x ANDed with x is x. Same thing. If you take something and you AND it with itself, you get the same thing. Okay. All right. What about the complement? X ORed with x complement is 1. Why is that? Who can tell me a simple reason for that? I mean, a logical reason for that. Because who can tell me?
If it's x was 0, it will become 1. If it's 1, it will become a 0. Both cases will have a 1.
Excellent. So in either case, x or x complement will be a 1. Okay. So if you OR these two quantities, you'll be guaranteed to have a 1 in one of them, exactly one of them, not all, not both. Okay. So in either cases, you have the OR operation equals 1. What about the dual of that? It's going to be x ANDed with x complement, and the answer to that is 0. And the same reason applies here. Okay, because one of them is going to be a 0 and one of them is going to be a 1, and ANDing of these will result in a 0. Okay, as I told you last time, you can think of the AND as multiplication operation. Okay, but or you cannot think of it as an addition operation. It's not like that. Okay, the AND is okay to think of it as just a multiplication operation, as long as we are talking about 1 bit. Okay, but once we start talking about bitwise AND, okay, then this is not the case. Okay, so what about commutativity? Commutativity means that if you have x or y, then it is the same as y or x, and the dual of that is x ANDed with y is the same as y ANDed with x. Okay, associativity, again, it's if you take x or y and take the result of that and OR it with z, then it's the same as x ORed with the result of y or z. Okay, and this is the dual of that is going to be x y ORed with z. I mean, no, not ORed with. ANDed with z is equal to x ANDed with y z. Okay. What about the distributive law? The distributive law. Okay. If you have x ANDed with y or z, what does this tell you? You can distribute x over the two literals here. So the x, the answer will be xy ORed with xz. Okay. And the dual of that is going to be x or yz. Okay, you don't need the parentheses here because the AND has higher precedence than the OR. Okay, is equal to what? X or y. Here you need parentheses because of the precedence. Same reason, x or z. Okay. All right. What about absorption? Absorption law, okay, is this. So you have x ORed with xy is equal to x itself. Okay, so who can tell me how can we prove this using the relations that we learned about last time? I mean, these we can use a couple of these properties, or these maybe, okay, to prove this one here. Okay, So what does this equal to?
X ORed with X,
Okay.
parentheses,
Okay.
X ORed with Y, I think.
Actually, this is so if you take X as a common factor here, okay, if you take X as a common factor, so basically you have here, yeah. So let me do it here, okay. So this is X ORed with XY, right? You can say, well, this is by the identity is equal to X ended with 1 ORed with XY, right? Yeah, and this is equal to, using the distributive law, I can take X as a common factor, and then this is going to be 1 ORed with Y. And then by the null law, I know that 1 or Y is what? Is 1, right? And then by the identity law, I can say this is equal to X. Okay? Do you see how? So then you can say, well, this is because of identity. Okay, and then this is distributive law, and then again null. Okay, and then identity. Okay, so this is a justification of each step. Okay, so you can see that we have proven using the previous things that we learned that this is nothing but X. Okay, so you can also see that using the truth table. So if we see, let's do the truth table of this expression here, XY, and then we have XY, and then we have X ORed with XY. Okay, so we have 0, 1, 0, 1, and then 0, 0, 1, 1. Okay, so this is going to be 0, 0, 0, 1, and this is going to be 0, 0, and then what? 1, 1, right? Compare this, okay, with this. Aren't they equal?
Yes.
Yeah, so this also proves the equality of the two terms, okay? So proving by truth table can be done also, but sometimes we ask you to prove using manipulations, okay? Boolean algebraic manipulation, okay? So continuing, okay, so what? Who can tell me what is the dual of the absorption law? Come on, guys. What is the dual? This is the law I'm talking about, the absorption law. What is the dual of this law? Wake up. X.
X
Uh-huh.
and X
And
X or Y.
like this.
Yes.
Just that is equal to
Is equal to I don't know.
X.
Oh, X.
This is a big mistake. No, wrong.
Oh,
Why?
Why?
Because you missed the brackets.
Oh.
Okay, so there has to be brackets here. Okay, otherwise it's not going to be correct because this, okay, does not equal, actually it does not equal to XX ORed with Y. which the x ordered with y is x or y. However, this quantity is, we have proven that it is x. Okay, and this quantity that you said, okay, is x or y. All right, so please make sure that you mind the precedence, okay, as you create the dual. Okay, so this is going to be x ended with bracket x or y is equal to x. Okay. Okay, what about the minimization law? So now if I ask you to prove absorption law, then you have to use the simplest, the other simple rules to prove it, okay, like identity and null and idempotence and stuff like that, okay? However, if I ask you to minimize a given logic expression, then you can say by absorption law immediately. If you have a similar expression to this, okay, then you can transfer to this, okay, and say in the justification, you can say by absorption law, okay? So you can use it to prove other or to justify your steps in the simplification. However, if I ask you to prove it, okay, to prove the absorption, then you have to use the simpler properties to do that, okay? Now, there is also the minimization law, okay? Minimization is xy ORed with x complement y, and the answer to that is y. If you take y as a common factor using the distributive law, you'll see that you will wind up with x or x complement ANDed with y. And x or x complement is nothing but 1, as we saw here, okay? So 1 ANDed with y is 1, as we saw here, okay? Which is the identity here, okay? So the dual of that is x ORed with y ANDed with x complement ORed with y is equal to y, okay? All right. Now the simplification rule, okay, we have seen it in example, I believe it was A's and B's, okay? So remember this example here. This one here, A, B complement ORed with B, we proved that this is nothing but A or B, okay? This is the simplification rule, okay? And we can prove it easily by, we will see next, okay? So this is what? The dual of that is x ANDed with x complement ORed with y, right? And this is equal to xy. This is the dual. So if the original expression is true, then the dual is true as well, okay? So you can use both the dual and the original expression to simplify Boolean algebraic formulas, okay, or expressions. So yeah, just a quickly, how can you prove that the simplification rule algebraically? Okay, just you can prove it by truth table, as we said in the example. This example actually does prove the simplification rule by truth table, okay? However, now we prove it using algebraic manipulation. So we have x ORed with x complement y, okay? And by distributive law, we can say this is equal to x ORed with x complement, right? ANDed with x ORed with y. And you say here distributive law, okay? And then this is equal to what? Using the complement law, okay? We say that this is 1 ANDed with x or with y, and this is by complement. And then this is equal to x OR with Y, because of what? Identity. Okay. All right. Do you see how we proved it? Okay. All right. Any question? Okay. So let's continue. We have also the consensus, which is we will prove later. Okay, inshallah. But right now, I want you to calculate the dual of that. Okay, the dual of the consensus is going to be x OR with y ANDed with x complement OR with z ANDed with y or z is equal to what? X OR with y ANDed with x complement OR with z. Okay, and that equal and of course this means that this is redundant here because it doesn't appear here. This is the same as this. Okay, however this is redundant. Okay, you can just remove it. When you do Boolean algebraic manipulation, you realize that by consensus theorem that this is redundant and you can remove it. Okay, also here you can see that this is equivalent to this. Okay, and you can see that this is redundant. Okay, now for De Morgan's law, you have x ORed with y, and then you take the complement is equal to x complement ORed with, ANDed with y complement. So what is the dual of that? Dual of that is x y complement is equal to x complement ORed with y complement. Okay, this is the dual of De Morgan's law. Okay, I think by now I think we finished the dual properties, the dual principle, as well as the basic identities. We will use these identities to prove or to simplify Boolean expressions. Now, regarding the quiz, inshallah, it will start at 11:30 exactly. However, I will add a 20 minutes lecture, okay, which will be which will replace the 20 minutes that we missed for the quiz. You don't have to attend that, but you have to listen to it. Okay, you have to listen to it at your own time before the next lecture. Okay, it is very important that you listen to it because I'm going to do some exercises in Boolean algebra. So let me stop here and see if you have any questions. No questions. This is, by the way, this is a lot to take. You have to go back and digest it very well. Okay. All right. So just to confirm that you understood, I will, in addition to this lecture, which is 30 minutes, okay, I will upload about 30 minutes. I will upload another 20 minutes, okay, additional, okay, which will cover some Boolean algebra. So I'll cover these examples, okay, Boolean algebraic manipulation, some examples of these. So you have to watch the video on your own before you come to the next lecture, okay? Maybe this video you understand, so you can skip it, but the other video, there is no way that you understand because you haven't seen it, okay? So it will replace the time taken by the quiz from the lecture, okay? All right, let me stop recording.